The octal numeral system, or October for short, is the base 8 number system, and uses the digits 0 to 7. Octal numerals can be made from binary numerals by grouping consecutive binary digits into groups of 3. For example, the binary representation for decimal 74 is 1,001,010, which can be grouped into 1,001,010, so the octal representation is 112. In the decimal system, each decimal place is a power of 10. For example, in the octal system, each place is a power of 8. For example, by performing the calculation above in the familiar decimal system, we see why 112 in octal is equal to 64 plus 8 plus 2 equals 74 in decimal. Usage by Native Americans. The Yuki language in California and the Pameen languages in Mexico have octal systems because the speakers count using the spaces between the fingers rather than the fingers themselves. By Europeans, it has been suggested that the reconstructed Proto-Indo-European word for 9 might be related to the Pi word for new. Based on this, some have speculated that Proto-Indo-Europeans used an octal number system, though the evidence supporting this is slim. In 1668, John Wilkins, in an essay towards a real character and a philosophical language, proposed use of base 8 instead of 10, because the way of dichotomy or bipartition being the most natural and easier kind of division. That number is capable of this down to n unite. In 1716, King Charles XII of Sweden asked Emanuel Swedenborg to elaborate a number system based on 64 instead of 10. Swedenborg, however, argued that for people with less intelligence than the king, such a big base would be too difficult, and instead proposed 8 as the base. In 1718, Swedenborg wrote a manuscript, NNY Rekenkonst som omväxlas vid talet 8 istället then 1 ligger vid talet 10, which changes at the number 8 instead of the usual at the number 10. The numbers chapters 1 to 7 are there denoted by the consonants L, S, N, M, T, F, U and 0 by the vowel O. Thus 8 equals lo, 16 equals so, 24 equals no, 64 equals lu, 512 equals lu, etc. Numbers with consecutive consonants are pronounced with vowel sounds between in accordance with a special rule. Writing under the pseudonym Heros or Apicim in the Gentleman's Magazine, July 1745, Hugh Jones proposed an octal system for British coins, weights and measures. Whereas reason and convenience indicate to us an uniform standard for all quantities, which I shall call the Georgian standard, and that is only to divide every integer in each species into 8 equal parts, and every part again into 8 real or imaginary particles, as far as is necessary. For though all nations count universally by tens, yet 8 is a far more complete and commodious number, since it is divisible into halves, quarters, and half-quarters without a fraction, of which subdivision 10 is incapable. In a later treatise on octave computation, Jones concluded, "Arithmetic by octaves seems most agreeable to the nature of things, and therefore may be called natural arithmetic in opposition to that now in use by decades, which may be esteemed artificial arithmetic." In 1801, James Anderson criticized the French for basing the metric system on decimal arithmetic. He suggested base 8, for which he coined the term octal. His work was intended as recreational mathematics, but he suggested a purely octal system of weights and measures, and observed that the existing system of English units was already, to a remarkable extent, an octal system. In the mid-19th century, Alfred B. Taylor concluded that our octonary base 8 radix is, therefore, beyond all comparison the best possible one for an arithmetical system. The proposal included a graphical notation for the digits and new names for the numbers. suggesting that we should count un, do, the, fo, pa, she, ki, unti, unti-un, unti-do, and so on, with successive multiples of 8 named unti, duty, the t, foty, patty, seti, kitty, and under. So, for example, the number 65 would be spoken in octonary as under un. Taylor also republished some of Swedenborg's work on octonary as an appendix to the above-cited publications. In fiction, in the 2009 film Avatar, the language of the extraterrestrial Navi race employs an octal numeral system, probably due to the fact that they have 4 fingers on each hand. In the TV series Stargate SG-1, the Ancients, a race of beings responsible for the invention of the Stargates, used an octal system of mathematics. In the tabletop game series Warhammer 40,000, the Tau race use an octal number system. In computers, octal became widely used in computing when systems such as the PDP-8, ICL 1900 and IBM mainframes employed 12-bit, 24-bit or 36-bit words. Octal was an ideal abbreviation of binary for these machines because their word size is divisible by 3, so 4, 8 or 12 digits could concisely display an entire machine word. It also cut costs by allowing Nixie tubes, 7-segment displays, and calculators to be used for the operator consoles. Where binary displays were too complex to use, decimal displays needed complex hardware to convert radices, and hexadecimal displays needed to display more numerals. All modern computing platforms, however, use 16, 32, or 64-bit words, further divided into 8-bit bytes. On such systems, 3 octal digits per byte would be required, with the most significant octal digit representing 2 binary digits. Octal representation of a 16-bit word requires 6 digits, but the most significant octal digit represents only 1 bit. This representation offers no way to easily read the most significant byte, because it's smeared over 4 octal digits. Therefore, hexadecimal is more commonly used in programming languages today, since 2 hexadecimal digits exactly specify 1 byte. Some platforms with a power of 2 word size still have instruction subwords that are more easily understood if displayed in octal. This includes the PDP-11 and Motorola 68000 family. The modern-day ubiquitous x86 architecture belongs to this category as well, but octal is rarely used on this platform. Although certain properties of the binary encoding of opcodes become more readily apparent when displayed in octal, e.g., the modern byte, which is divided into fields of 2, 3, and 3 bits, so octal can be useful in describing these encodings. Octal is sometimes used in computing instead of hexadecimal, perhaps most often in modern times in conjunction with file permissions under Unix systems. It has the advantage of not requiring any extra symbols as digits. It is also used for digital displays. In programming languages, octal literals are typically identified with a variety of prefixes, including the digit 0, the letters O or Q, the digit-letter combination 00, or the symbol $and or $. In Motorola convention, octal numbers are prefixed with it, whereas a small letter O is added as a postfix following the Intel convention. Dr. DOS debug uses to prefix octal numbers. For example, the literal 73 might be represented as 073, 073, Q73, 0073, 73, at 73, and 73, $73 or 73 in various languages. New languages have been abandoning the prefix 0, as decimal numbers are often represented with leading zeros. The prefix Q was introduced to avoid the prefix O being mistaken for a 0, while the prefix 00 was introduced to avoid starting a numerical literal with an alphabetic character, since these might cause the literal to be confused with a variable name. The prefix 00 also follows the model set by the prefix 0x used for hexadecimal literals in the C language. It is supported by Haskell, OCaml, Perl 6, Python as a version 3.0, Ruby, TCL as a version 9, and it is intended to be supported by ECMAScript 6. Octal numbers that are used in some programming languages for textual, graphical representations of byte strings when some byte values have to be 2. Escaped as NNN. Octal representation of non-ASCII bytes may be particularly handy with UTF-8, where any start byte has octal value 3NN and any continuation byte has octal value 2NN. Conversion between bases. Decimal to octal conversion method of successive Euclidean division by 8 to convert integer decimals to octal. Divide the original number by the largest possible power of 8 and divide the remainders by successively smaller powers of 8 until the power is 1. The octal representation is formed by the quotients, written in the order generated by the algorithm. For example, to convert 12,510 to octal, 125 equals 82 times 1 plus 61. 61 equals 81 times 7 plus 5. 5 equals 80 times 5 plus 0. Therefore, 12,510 equals 1758. Another example, 900 equals 83 times 1 plus 388,388 equals 82 times 6 plus 4. 4 equals 81 times 0 plus 4. 4 equals 80 times 4 plus 0. Therefore, 90,010 equals 16,048. Method of successive multiplication by 8 to convert a decimal fraction to octal. Multiply by 8. The integer part of the result is the first digit of the octal fraction. Repeat the process with the fractional part of the result, until it is null or within acceptable error bounds. Example. Convert 0.164065 to octal. 0.164065 times 8 equals 1.3125 equals 1 plus 0.3125. 0.3125 times 8 equals 2.5 equals 2 plus 0.5. 0.5 times 8 equals 4.0 equals 4 plus 0. Therefore, 0.16406510 equals 0.1248. These two methods can be combined to handle decimal numbers with both integer and fractional parts, using the first on the integer part and the second on the fractional part. Octal to decimal conversion. To convert a number k to decimal, use the formula that defines its space 8 representation. In this formula, I is an individual octal digit being converted, where I is the position of the digit. Example. Convert 7,648 to decimal. 7,648 equals 7 times 82 plus 6 times 81 plus 4 times 80 equals 448 plus 48 plus 4 equals 50,010. For double-digit octal numbers, this method amounts to multiplying the lead digit by 8 and adding the second digit to get the total. Example. 658 equals 6 times 8 plus 5 equals 5,310. Octal to binary conversion. To convert octal to binary, replace each octal digit by its binary representation. Example. Convert 518 to binary. 58 equals 10, 12, 18 equals 0012. Therefore, 518 equals 101, 0012. Binary to octal conversion. The process is the reverse of the previous algorithm. The binary digits are grouped by threes, starting from the least significant bit and proceeding to the left and to the right. Add leading 0s to fill out the last group of 3 if necessary. Then replace each trio with the equivalent octal digit. For instance, convert binary 1,10,111,100 to octal. Therefore, 10,101,111,002 equals 12,748. Convert binary 11,100.01001 to octal. Therefore, 11,100.01012 equals 34.228. Octal to hexadecimal conversion. The conversion is made in two steps using binary as an intermediate base. Octal is converted to binary and then binary to hexadecimal, grouping digits by 4s, which correspond each to a hexadecimal digit. For instance, convert octal 1057 to hexadecimal, to binary, then to hexadecimal. Therefore, 10,578 equals 22F16. Hexadecimal to octal conversion. Hexadecimal to octal conversion proceeds by first converting the hexadecimal digits to 4-bit binary values, then regrouping the binary bits into 3-bit octal digits. For example, to convert 3FA516 to binary, then to octal. Therefore, 3FA516 equals 376,458.